Hey ladies and gentlemen, here we are with the answers to worksheet 1. The first couple questions here are pretty easy. You just have to use the conversions between one unit of pressure and another. So I've got the dimensional analysis down there. Looks like I left my decimal out on this one. Sorry about that. Um, so you pick the two things that are equal to each other in the first question, talking about millimeters of mercury in atmospheres. One atmosphere is 760 millimeters of mercury, so we've written that as a ratio here. And then in the second one, we're using the same ratio but in reverse. Remember, the key is to write down units when doing dimensional analysis so that you can set things up. And then we just multiply and divide as written. Alright, here we go. Now we're actually doing some word problems involving gas laws. This first gas law is what we call Boyle's law. It's Boyle's law because we have a volume and two pressures, and we're looking for the new volume. And Boyle represented how that law was inversely proportional. If the volume was going down, the pressure was going up. That's what inverse means, is that the two values should be moving in opposite directions. So here we see the pressure is going from 1 atmosphere to 2.18 atmospheres. So since the pressure is going up about double, we should anticipate that the volume goes down by about half. Up by double, then down by a half. So we plug the values into the equation. PV equals PV equals PV. Here are the values. Solve for the new volume. Here we go. All of these numbers happen to have three significant figures, so our answer also has three significant figures. Number 5 is pretty much the same type of question. It's in millimeters of mercury. That's fine. You could leave it in millimeters of mercury. I have chosen to switch it to atmospheres just because I prefer atmospheres. If you didn't, your answer would be a lot bigger than 20 atmospheres over here. The other issue with this one is that the volumes are in slightly different units. This is in liters and that's in milliliters. So I chose to take the milliliters and divide by 1,000 to convert it over to a liter, to liters. So I took 50 milliliters, divided it by 1,000, and now it's in liters. In number 6, we've got volumes and temperatures, and this is called Charles' Law. Look at that beautiful handwriting right there. The most common wrong answer is this one right here, 14.7. 14.7. How do people get this wrong? They've got the equation, V over T equals V over T, and the numbers, 25, 26, 15, and they just plug them in straight. The problem with these temperatures is they're not actually measuring energy like Charles' law is meant to measure. So we have to convert the temperatures into the absolute scale, the Kelvin scale, which is a simple addition problem. To go from Celsius to Kelvin, you add 273, which seems like a pretty random number. So you go from Celsius to Kelvin, we add 273, and then it will predict the new volume correctly. So here are our initial volume and initial temperature and our new temperature. You can see in the Kelvin scale that we really just have a slight decrease in temperature, so we're going to have a slight decrease in volume. But in the Celsius scale, it looks a lot bigger because we're not really anywhere near the lowest possible temperature, but we're tricking ourselves with Celsius. And that's Charles' law. Remember, convert to Kelvin. How often should I convert to Kelvin? Oh, just every time. That's it. Just always. Okay? Number 7, we have moles of argon and a volume, and we have new moles and volume. Oh, this is Avogadro's law. Yep, good old Avogadro. Avogadro's law. There we go. Avogadro was measuring moles in volume, or how much gas is in there. Remember, moles are a way of expressing how much stuff, actual particles floating around. So we've got the volume at 652, and then the two different moles. Plug and chug. Since I left this in milliliters, my answer initially comes out in milliliters, but that seems kind of silly, so I divided it by 1,000 to get to liters. All right, what else we got here? Number 8, again, this is the moles are changing and the volume is changing, the temperature is not changing. So this is another Avogadro's law. Just plug the numbers in carefully, cross multiply, so that'd be 11.2 times 2. When we cross multiply this over, divided by 0.5, we get, it's increased to 44.8. That also makes sense. They went from 0.5 moles to 2 moles. That's 4 times the number of moles. So if you blew 4 times the amount of gas into a balloon should get 4 times bigger, which is what we're seeing here mathematically. Now, number 9 is our first ideal gas law problem. How do I know it's an ideal gas law problem? We have a temperature. Here we go. We have moles. We have atmospheres. We have volume. None of them are changing. It is 4 variables, 4 different values. None of them are changing. Excuse me. And we're trying to figure out the missing one, which in this case is temperature. So I have written down values I was given. Pressure was in atmospheres, volume, moles, and then we have R. R is a gas constant that unites the other 4 together. And one of the trickiest parts about R is there's different ways of measuring R. Almost everyone always measures volume in liters, and of course moles are in moles, and temperature has to be in Kelvin every single time. But pressure has 3 common units associated with millimeters mercury, atmospheres, kilopascals. Oh, remember these two, millimeters and torr, are really the same thing. So I guess there's 4 units, millimeters mercury, torr, atmospheres, and kilopascals. And in the notes, we discussed the different R values. And so since this was in atmospheres and this version of R is also in atmospheres, I picked that version of R, the 0.08206, so that the units could be united around R. Plugged them into PV equals nRT, pressure in atmospheres, volume in liters, moles, 0.08 up, around it a little bit. Sorry there, folks. Here we go. And I got a temperature that is 45 kelvins. 45 kelvins would be what on the Celsius scale? Let's see, 45 minus 273. That would be negative 227 Celsius. Yeah, that's cold. Negative 227 Celsius. It doesn't say it has to be in Celsius. It just says what temperature. So solving in Kelvin is perfectly legit. The only I would not accept Fahrenheit. If you decided to convert Celsius to Fahrenheit afterwards, that would just be ridiculous. Leave it in Kelvin though. It doesn't say it can't be. Number 10, also an ideal gas law problem. The big trick with this one though is, well, there's 2 tricks, but first they've given us mass. And masses are not very useful to chemists. We spent a whole chapter converting masses into moles. A couple back, it was chapter 6. So that's the initial thing I've done here, is I have taken these 5 grams of neon and converted them to moles of neon. Do that first. Here we go. They are 0.248 moles after the conversion occurred. Secondly, the pressure was in torr, so we have to pick the R value that is in torr. So I went to the notes and I looked up R is 62.36 liters torr moles Kelvin. So now I can plug all these values into my PV equals nRT and solve for T. There's the torr, there's the volume, there's the moles, there's the R in these units, and I solve for Kelvin. Again, that's not a very hot Kelvin. That's the ideal gas law. How do I know which one to use? Look at the units. Grams are useless, convert them to moles, liters, torr, temperature. Feels like a PV equals nRT to me. Number 11, I know I'm going pretty fast. Sorry about that. Kind of pressed for time. But we have volume and temperature and pressure. We have all 3. We have a new temperature, new pressure. What's the new volume? So we have 3 values and we have 3 new values. This is what we call the combined gas law, where they combine Boyle's law, PV equals PV, and Charles' law, V over T equals V over T, and Gay-Lussac's law, P over T over P over T, all together into one, and it works pretty well for ideal gases like oxygen and noble gases like neon, regular gases like nitrogen. So we have volume, change the temperature to Kelvin always, pressure matches in units, that was negative 40, plug them all in, and we have a volume change. Looks like the volume went down by about half. Why did the volume go down by almost half? Well, the temperature decreased, that should decrease the volume. The pressure increased. Remember from Boyle's law, if the pressure increases, the volume should decrease. This double of the pressure cut the volume in half, so we went from 1 atmosphere to 2, so we should go from 500 to 250. So right there, that's your 250. And then the temperature also decreased. If you get the temperature colder, the volume should also go down. So that's why we have an additional drop from 250 to 204. Number 12, also known as the easiest question. You have two gases in the same container. What's the total pressure? Just add them together. That's the total. No, really. I did that in my head. It's not hard. Just add them up. This is called Dalton's law of partial pressure. Number 13 can be done the same way, but I've chosen to do it a much easier way. We have masses. Again, masses are so completely useless to a chemist. We are going to immediately convert these masses into moles. I did not show the work, but I think you can take 50.1 grams, go to the periodic table, and convert it to moles. Spoiler alert, that's it right there. 26.2, yep, I just recorded that noise. 26.3 grams of nitrogen, converted, there's the moles. Add them up, we have all of the moles of gas. This is oxygen and nitrogen. They're mixed together just like the room you're sitting in right now, unless something weird has happened to the room in my absence. We can add these two together, and we have the total moles, which we can just use as the moles. We have the volume. I have picked this R. Why did you pick this R? I don't know. Kind of like that R. It's really fun to say. 0.08206. No, it's just one of the more common R's. Since this R is in atmospheres, when we do all of the math, PV equals nRT, the atmosphere unit won't be canceled, so it comes out with that one. I'll explain these two in a second. Hey, Celsius, that's useless. Convert it to Kelvin. PV nRT, divide the 25 this way, so P equals these things divided by 25. And if we use this R, we get this for pressure. But you have other choices. You could have used 8.3145. That would give you kilopascals. Or you could use 62.36 for R, and you'd get millimeters of mercury. Which answer is the right answer? All of them, any of them. Just write down which value for R and the units in your answer, and you have answered this correctly, because there's different ways of measuring pressure. I know that seems confusing, but aren't there different ways for measuring distance? Couldn't you measure distance in millimeters, or feet, or miles? And pretty much people pick the unit based off of the distance. If you're only walking a short distance, you would probably measure it in inches or centimeters. If you're walking a longer distance, you'd probably measure it in feet or in meters if you wanted to do it metrically. And if you were running a long distance, you'd probably measure it in miles or kilometers. Well, we do the same thing in chemistry. We pick the unit that makes the easiest to imagine. I have no trouble imagining 2.5 of something. So atmospheres probably makes the most sense. Very few people can imagine 1870 of anything. So millimeters of mercury doesn't make terrible good sense here as a choice. Kilopascals is actually the standard unit across all of science. So if you were writing an answer in a scientific journal, this should be the right answer. But for our sake, any one of these answers. I have spent a lot of time talking about R here. Let's go on. 14 and 15, I don't think we got to this in every class. It's actually a pretty simple concept. If you plug some standard values, and this STP stands for, or represents, I should say, so I don't use a word in the definition. STP represents standard temperature and pressure. Standard temperature is 273 kelvins, which is also the value we add from Celsius to Kelvin. Standard pressure is 1 atmosphere. So this 273 and 1 are considered the standard values, and if you plug those into the ideal gas law, you always get this constant relationship between moles and volume. Since you wouldn't be changing the temperature and the pressure, the only two units left are moles and volume. And we find the ratio is for every 1 mole, there's 22.4 liters of gas. So in 14, we have 2.02 grams of hydrogen. That is 1 mole. So 2.02 grams, which is 1 mole, should be 22.4 liters. But that seems a little too simple. So let's use the ideal gas law to also show that. So here's the ideal gas law, PV equals nRT. Let's plug in standard pressure, 1 atmosphere. We don't know the volume. We know that 2.02 grams is 1 mole. Here I've picked R. Guess why I picked this R? I picked it because the atmospheres have to match. And Kelvin. So we plug these values in, bam, 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 divide the 1 over, we get the volume's 22.4. So now we've kind of supported the fact that at STP, we know the volume. And then number 15 is the exact same thing, just in case you weren't paying attention. 32 grams of oxygen would be 1 mole, therefore that's 22.4 liters. If it hadn't been exactly 32 grams, say if it was 24 grams of oxygen, we could say, well, 24 grams of oxygen is 3/4 of a mole. That's 3/4 of 22.4. We could apply it ratio-wise. All right. Tell me whether the following assumptions are true or false for an ideal gas based on kinetic molecular theory. Kinetic molecular theory was what we started off with. These are the general ideas behind all gas laws we assume to be true. So let's go. Molecules are assumed to have 0 volume. We do assume this. We assume that their volumes are so ridiculously small that they might as well be 0. The kinetic energy of the system is conserved. We also always assume this, that when the particles collide together, the total energy is still the total. So we're not going to lose any energy to the surroundings. Molecules show attraction to each other. This one is false. In kinetic molecular theory, we do not think that the molecules are attracted to each other. We pretend that all molecules of gas particles are completely non-polar. That is to say, they just bounce off of each other perfectly. So that third one there is our false one. Fourth one, gas particles move in a straight line. That is the other assumption we make. We pretend that gravity and other interactions with the universe are ignoring these gas particles. And for the most part, they are. The mass of a gas particle, one gas particle at a time, is so small, the gravitational force on it is practically nothing. It will pull it back down to Earth, but it might take a long time because the force of gravity is really having trouble exerting any force on these gas particles. And the fifth one, each molecule has the exact same energy as every other molecule. This is not true. This one's false. They don't all have the same energy, but they have the average is proportional to the temperature. The average of the entire gas set is proportional to the temperature. But they're not all moving around with the same energy. Okay, there are the answers to your homework. I hope you understood. Feel free to watch this again and again, especially if you're having trouble sleeping. And good day to you.